Okay, welcome to lecture 10.2. Okay, let me now explain what Kurt Signorino calls the crisis game. Okay, so by the way, so this is Kurt does quantitative methods, game theory within a political science department. But he's also kind of within that he usually looks at international relations. So countries deciding whether to go to war or not with each other. Now, um, within international relations, I'm not sure why it happens, but instead of calling it countries, they call each other the country states. So, state one goes against state two. So I'll follow that, but it's really countries. So in this game, there's in the crisis game, there are two states or two countries. Okay, and in the way it works, in the first period, state one, some crisis comes up, and the state one has to decide whether it wants to fight country state two or not fight. And so we label this. If it decides to fight, we label it F1. Decides not to fight, we label it F1 bar. Okay. Now, next, if state one decides to fight, then country two. Draw this symmetrically. My my hand feels good. I'm not writing that well, though. Yeah. Okay. So if it decides to fight, country two gets to move, and it chooses whether to fight. We call that little f2, or not fight, little f2 bar. Okay, if they go down this branch, then this branch, the outcome, we call that outcome W1. And what that means is a war where country one started the war. Okay. Now, if they go down this branch, then this branch, Signorino calls it outcome C2. And what this means is it's capitulation, and state two capitulated to state one. Okay, now, they go down this branch. Number one chooses not to escalate, chooses not to invade state two. State two gets to move, and oh wait, you know what? I'm sorry. I did these wrong. Oh, man, I'm looking at my notes. This was called F3. And we're going to use F2 over here. So if we go down this branch, state 2 gets to move, and state 2 decides whether to fight or not. If it fights, we call it F2. If not, we call it F2 bar. Okay. If we go down this branch, then this branch, we call the outcome the status quo. Okay, so this is peace. Okay, and so neither one invaded the other one. Now, if go, okay, now if we go here, then here, all right, state 1 gets to move again. So here, state 1 has chosen not to escalate, but then state 2 did escalate. So I think this is like state 2 has sent troops to the border of state 1. So state 1 has to choose whether to fight or not. And then state 1 does fight, we call it big F sub 4. If state 1 does not fight, we call it big F sub 4 bar. So we go down this branch, then this branch, then this branch. This is war. And it's a war started by country 2. Okay, now if we go down this branch and this branch and this branch, what happens is that state 1 has capitulated, and so we call it C1. Okay, capitulation. The capitulation was done by state 1. Okay, so that is the game. Let's see. Okay. Yeah, I'll keep going. Okay, I thought I might end this video, but no, I'm gonna keep going a little bit more. Okay. Now, first thing we want to do is we are going, let's see, P4. Okay. We're going to examine this node right here. Okay. So, what we're going to do is we're going to try to estimate or put an equation to describe the probability that if we reach this node, what's the probability that state 1 is going to choose F4? Okay, so what we're going to do is we're going to talk about state 1's utility of W2 versus state 1's utility of C1. And we're going to call U of those their scene utility. And then we're going to add an error term. What's the error term going to be? Weibel. Okay. And then we're going to use the McKelvey-Palfrey trick. So they remember last time I talked about the agent QRE model. And so what we're going to do is assume, so we're going to have error terms on these utility functions. And in theory, we would say, well, one chose this branch, and probably because one knew something about, let's say we'll call it her own error terms on these utilities, okay? But the agent QRE model says, no, we won't do that. We're going to treat this person at state 1 at this node as if it's a different agent of state 1. So in this case, the agent of state 1 or country 1 is the Secretary of State. In this case, it may be the Secretary of War. And they don't know each other's error terms, and that makes it simpler. Okay, so that's where we're going. Okay, but the key is we're going to state a probability term of the probability that 1 chooses big F4, goes down this branch. Okay, so that is where we're going. Okay, so let's define it. Okay, P4 equals, defining it, this is probability 1 chooses F4, comma, given 1 chose big F1 not, and 2 chose little f2. Okay, so what that means, just going back, all it means is a P4 is a probability that one chooses this branch, given that we've gone down this branch and then this branch. Okay, that's all we've done. Okay, that is P4. Now, here's what we're going to do. All right. We're going to define utility. U substate 1. We're going to call it star. That's what Kurt does. This equals U1 of W2. All right, so U1 without the star is going to be the scene utility, okay, plus epsilon 1 W2. Okay, and then wait. Oh, sorry. W2. Okay. U1 star of W2 equals that. U1 C1 equals U1 star equals U1, the scene utility, plus epsilon 1 of C1. Okay, now what we're going to do is the McFadden trick, which means we're going to assume that the error terms are Weibull. Okay, then once we do that, we have a very easy form of what that probability is. The probability that this utility is bigger than that utility. And so you should know that. This just equals E to the U, the probability that one chooses F4, which means the war. That's the W2 branch. That equals U, the scene utility, U1, W2, so P4 equals times divided by E to the U1 W2 plus E to the U1 C1. Okay, now, so that is the formula, but I've left something out. Okay, now if you remember from McKelvey-Palfrey, what they do is they multiply all the scene utility. So in the case of their first paper, when the scene utility was the payoffs that the researcher is giving in the experiment, so the money that the people receive, the error terms were this psychic utility. So how much extra enjoyment you get out of playing action A1 rather than action A2. Okay, those are the error terms. Okay, now if you remember McKelvey-Palfrey, they multiply the money payoffs by lambda, and then they say that lambda is a parameter that expresses the rationality. Okay, so it's how much weight they place on the scene payoffs versus this psychic utility. Okay. So Kurt Signorino is going to do the same thing. He's going to multiply the scene payoffs by lambda. Okay, and so that's what we get. So now here's the McFadden trick. So the probability, P4, is just lambda times U of W1. We're talking about U of W1, U1 of W2, and U1 of C1 in a second. Okay, but for the moment, we just put a lambda on those and then multiply it times the scene utility. Okay, let's see. What else am I going to describe? Why do we do that lambda? Okay, one reason that's important is because we assume that this Weibull term, the error terms are distributed standard Weibull. And so that means that probability, say this one, epsilon 1, W2 is less than or equal to Z equals I think I got this right, e to the minus E negative Z. Okay. All right. Okay, that's the CDF when it's standard Weibull. Now, you can't really make that assumption without loss of generality. So that is when we assume that standard Weibull rather than something else. Okay, and by the way, so instead of being standard Weibull, so we could have called it generalized Weibull. All we would do is just divide that Z by sigma. Okay, so sigma, it's not exactly the standard deviation, but it's proportional to the standard deviation. Okay, so when we assume that these things are standard Weibull, we're making an empirical assumption that has some empirical bite. We're assuming that that sigma equals 1. Okay. Now, what Kurt Signorino is doing is he's saying, well, okay, an alternative to what we could do is say, well, instead of assuming that sigma equals 1, we could just, turns out we can call it lambda, okay? And if instead we just make it a general lambda, and then we don't have a lambda in front of these scene utilities, okay? We just take, say they're money payoffs from an experiment or whatever they are. It turns out this form, assuming general Weibull, causes you to have to add that lambda onto the scene payoffs, okay? Think of it this way. This lambda, or 1 minus lambda, 1 over lambda, is in a sense the weight you put on the error term, okay? But really all that matters is the relative weight you put on the error term versus the relative weight you put on the scene payoffs. And so putting a weight of 1 over lambda on the error term is the same thing as putting a weight of 1 on the error term, but instead putting a weight of lambda on the scene payoffs. Okay, so that's what's going on here. Okay, so once we make this the scene utility, we generalize it. We say, well, we're going to multiply that by a constant lambda and estimate that lambda. Once we can do that, it's not it doesn't restrict our model anymore to assume those error terms are standard Weibull. Okay, so don't get too hung up on this, but the key is that to get this form like this, there's 2 ways to do it. One is to put to multiply the scene utility by lambda, okay? Assume the error terms are standard Weibull, okay? The other way to get the exact same form is not to put the lambda on these scene utility terms, but instead to assume the error terms are general Weibull, where the CDF is this form, where you just divide by lambda, okay? Either way gets you this form, okay? So that's what's going on here, okay? And there's 2 ways to justify it. So for now on, what I'm going to do is I'm going to use the language that Signorino uses in the paper. So, well, we're going to assume the error terms are standard Weibull, but we're going to add this constant lambda times the scene utility, okay? And we're going to talk later about whether you can interpret that as a parameter of how rational the actors are. Um, you can, but another way is just saying that lambda 1 over the lambda it tells you something about the standard deviation of the error term. That's another way of saying it. So I'm going to avoid saying it says something about how rational they are. Another way, although you could say it expresses the weight that the countries put on the scene utility versus how much weight they put on the error term, the utility involved in the error terms. Okay, now, given this, so this final thing, we've already got one result. So P4, this is equation 7 in Signorino's paper. Okay, so we're going to use that in a second. All right, so that was lecture 10.2. Okay, I'm going to continue this. Results from the Signorino model in 10.3. Okay, I'll see you there.